All right, so welcome. So we're doing lifelong robotic occupancy. The basic idea here is that we have a robot laser scanner right on the base of our robot, and it's able to observe, the fronts of things like tables, chairs, etc. But we want it to be able to do things like fill in the back of table, fill in the things like the back of chairs or other occluded objects, to be able to fill in the rest of the map, right? And this is in essentially the local area around the robot. So you can sort of see in this bottom right-hand corner here, you have a view of what an observation from the laser scan would look like, right? And then you can sort of see like the blob sort of map that we wanted to emit from this machine learning model versus, say, a ground truth. So the way this works is we basically have a two-stage process. In stage one, right, we configure the environment with some random configuration, and we do a manual mapping phase. This is simply an engineering choice to allow us to get a good visualization, right? You can see in the upper left-hand corner here, this gray and black ground truth map. And this is also what we use as the supervisory signal when we're ultimately actually training this model. And then you can see what the model is actually emitting is shown in green and purple, right? The green is free space, and the purple is actually the estimates of what we think is structure. And you can sort of see as this robot's driving around, right, it's able to see the front side of this table over here, and it's actually able to do a proper fill-in of the back and sides of the table because it's learned through experience over multiple lifetimes what general structure of tables looks like, right? It's able to generalize this across these various lifetimes, which are the various configurations of the robot. And that's being done in this second autonomous mode here. So that's currently what's happening because the robot is wandering around doing the forward pass of our trained model on the robot while additionally collecting this data to then do continual learning. And so for the continual learning piece, you can see in this upper right-hand corner here, these are a tensor board. And you can see basically multiple lifetimes worth of, or multiple batches over multiple lifetimes of our robot training. And basically what's going on here is it's basically taking both its current experiences plus functional regularization using prior experiences in order to learn to do this generalization. Another neat thing is, and this is not directly visible in any of our visualizations, but we're actually able to do not just estimates of what's there, we're also able to be doing uncertainty estimates of how certain are we that our structure is good or not. So a concrete application domain for something like this is if you're trying to do exploration of new environments, right? What we're training is a model that's able to take multiple experiences of multiple lifetimes and zero-shot a new environment. And this is used for something like exploration, right? I have a house I've never seen before. You could run just a traditional SLAM package with some sort of exploration, like random walk or something else. But you can do better than that if you're able to use your prior experiences to inform you what structure you've seen before and estimate it, right? So if you see the front half of a table and you've seen lots of tables before, you don't need to go look at the back side of the table, right? If you have another room, right, with some odd geometry, you want to know that even though you're able to do a fill-in of what's behind there, you're not certain about it, and you should actually go look behind there. So that's one of the neat things that's happening with this sort of ensemble. And so actually all four models for our ensemble is being run on the Jensen Xavier. That's the little black computer that's running in the front there. And we're actually streaming the outputs of those to this Argus display on the screen.